Okay, let's get started. So project number 4 is due Friday, March 20th. We will continue with chapter 3 today, maybe start chapter 4. Are there any questions? Okay, we left off last time on page 359. So we're talking about proportional odds regression models. They are models that are useful when you have a multi-category response that where there's some kind of ordering amongst the categories. So in terms of one variable, one explanatory variable that is, this is what our model will look like, where we model the logit of the probability y is less or equal to j. In other words, this is the log odds, where the odds is with respect to a cumulative probability. We set that equal to beta j0. Notice the j that's in there and how it matches the j that was on the left-hand side of the model, plus beta 1 times x. And again, that is correct that there is no j in that beta 1. And that's what gives us the proportional odds part, as we discussed before. So now we'd like to be able to interpret the effect that x has on the response. And so what we're going to do is essentially use the same techniques that we did in chapter 2 for logistic regression model, except for now our odds that we're working with is a little bit different from what we had in chapter 2. So of course then we could, and we've actually done this before, we can find the probability y is less or equal to j over 1 minus the probability y is less or equal to j, and we set that equal to e raised to the beta j0 plus beta 1x. Okay, so what we've just done there is calculate an odds. Odds that you're in category category j or less versus more than j. And so if we look at this in the context of the explanatory variable, let's say a c unit increase of x, then we can form our odds ratio. And this is what it looks like. So the odds at x plus c divided by the odds at x. We write it out in terms of the model. Look what happens. We get some stuff canceling out as we did back in chapter 2. And we're left with just simply e to the c times beta 1. Should look very familiar. So notice that this odds is not dependent upon x at all. Also, notice that the odds is not dependent upon the level of j. So that can be helpful with our interpretations. So here's how you can interpret it. One way. The odds of y less or equal to j versus y greater than j change by e to the beta 1. Oops, I'm missing a c in there. Sorry. E to the c times beta 1 times for a c unit increase in x. So basically the same interpretation that we saw in chapter 2, except for how we define our odds there. Of course, in a real problem, you replace y with what it's actually measuring. But again, notice that j is in there, or j is represented here. But j is actually not in our actual number that we would form. And so it doesn't matter what you put in there for j, you're still going to have the same interpretation. So like with respect to the wheat example, whether j is representing the scab or the sprout level, it doesn't matter. It's going to be the same. Well, some notes then. This is on page 60. These notes basically come out of chapter 2, and that is if you have more than one explanatory variable, you want to interpret the odds ratio, well then you have to say holding all the other variables in the model constant. If you have some kind of interactions or transformations, well, the odds ratio is not going to be this simple form anymore. And again, essentially the stuff from chapter 2 is going to apply here. Same form of your odds ratios. And lastly, Wald and likelihood ratio-based inference procedures are available for these odds ratios. Unfortunately, the MC profile function is not going to help you because it cannot be used with output from the POLR function that estimates these models. So let's take a look at the weak kernels example and calculate some odds ratios. So if you remember with these weak kernels, again we have our levels of our response are, scab is less than sprout is less than healthy. That's our ordering. So j equal 1 is scab, j equal 3 is healthy. And similar to what we did with the multinomial regression model, we're going to look at a C-unit increase in each of the explanatory variables, and we're going to use one standard deviation for that C-unit increase for each of the explanatory variables. The one exception is with respect to the class of the wheat. Is it hard red winter wheat or soft red winter wheat? And so we'll just use C equal 1 since that is an indicator variable for soft red winter wheat. So let's say that we've estimated our model. We put the results into an object called ma.fit.ord, as we did last time actually. If I use the $ coefficients with it, that gives me almost my beta hats. I have to actually use a negative out in front of it to get the beta hats. Because remember, the model's not actually estimating, the function is not estimating our defined model.
Why do you have the minus C in front of the round as the...
Okay. This does come from earlier in the notes. All I did was just copy it. And remember what that does, it just removes column 1 and column 7. I only want the explanatory variables in columns 2 and 6. Columns 2 through 6. And so I take these beta hats now, after I've applied the minus sign there, times my C's. I use the exponential function with it, and I round them to make them look nice. So for example, with this density here, the one standard deviation is 0.13. So for a 0.13 increase, my odds ratio is 0.17. Let's more formally interpret that. Actually, what I'm going to do is invert the odds ratio so that it's above 1 for density. And I can say the estimated odds of a scab versus sprout or healthy. So again, J, this would be for y less than or equal to 1, and then y greater than 1. The estimated odds of a scab versus sprout or healthy response changed by 5.89 times for a 0.13 decrease, since I inverted the odds ratio, in the density, holding the other variables constant. You could do a similar thing for a weight. You could do a similar thing for all the explanatory variables. Do note that for the class variable, I forgot the holding the other variables constant part there. Just please make sure you put that in there. Now remember, J doesn't actually matter here. So I could also word this with the same numerical odds ratio, same number. I could also word this odds ratio here with density as the estimated odds of a scab or sprout versus healthy response, changed by 5.89 times for a 0.13 decrease. So in that particular case, then I'm saying y is less than or equal to 2 versus y is greater than 2. Now, because you get that exact same, essentially the same interpretation, then it's often better to make the following way to interpret these odds ratios. Please take special note of this. The estimated odds of a kernel quality being below a particular level, notice I'm not saying what level, I'm just saying a particular level, changed by whatever I get for my numerical value for the odds ratio, times for a, let's just say C unit, increase in, give me the explanatory variable name, holding the other variables constant. Overall, I think that's probably the best interpretation of it, because it covers all the cases.
So, in the interpretation, we're not only comparing to the adjacent category, but to all the other categories.
Well, remember, it's, we are modeling cumulative probabilities here. So that's why there's more than one category that's, I'm sorry, more than two categories that are listed in the odds ratio. But still, you have this, you're drawing the line somewhere. And so you could draw the line just at scab versus sprout and healthy. Or you could draw the line at scab and sprout, and draw the line versus healthy. And when you have an ordinal response like this, it makes sense to do that, because we have the ordering in the categories. You want to know, maybe what's the probability of being, 2 or less, essentially. Now, with respect to density, again, remember what we had saw in the parallel cornice plot. I'll let you look back on your own, and that was, the high density ones were healthy, medium were sprout, and then the low ones were the scabs. And relate that in that plot to what we just found with this odds ratio, that when you when you decrease that density, you're more likely to be of lower quality. Well, what about then profile likelihood ratio intervals? Well, unlike with multinomial regression models, you can use the confidence function. And this will allow you, just like what we did in Chapter 2, allow you to find some simple profile likelihood ratio intervals for first of all, for your betas, and then for your odds ratios. Again, we don't have access to MC profiles, so you're not going to be able to do complicated ones rather easily as you could with MC profile. Instead, what you would have to do is use walled intervals. I'll talk more about that shortly. So let's find my confidence intervals for the betas. So I use confident object equal mod.fit.org, then level 0.95. Now this is maybe not the best word here, conf.beta, because this is not actually a confidence interval for the betas, it's actually confidence intervals for those, remember, those etas. So be careful. Well, I mean, how do you get the confidence intervals for the betas? Well, just take minus what you get. So then if I want a confidence interval for the odds ratios themselves, again, I just multiply by the C value. I use the exp function again, and here are my confidence intervals. Notice again for density, it's 0.11 to 0.26. Notice 1 is not in that interval. So that's obviously very important, saying that density does matter. If I invert that interval for density, this is what I get, 3.87 to 9.36. And so that leads them to the following interpretation. With 95% confidence, the odds of a scab instead of sprout or healthy change by 3.87 and 9.36 times when densities decrease by 0.13, holding the other variables constant. Again, you could change this from just scab to scab and sprout. And then this could be changed to just healthy. You get exactly the same value. Or you could probably do a little bit better interpretation and say, the odds of being below a particular quality level of the kernel versus above it, change by, and then continue with interpretation. Well, what about wall intervals? Unfortunately, conf.int.default will not work here. If you remember, we used that in chapter 2 to find wall confidence intervals for a logistic regression model. Fortunately, it's not going to work here. So you're actually going to have to go back to the formula, to the actual equations, to figure out what they would be. And so, take note that you would need to do that for the more complicated cases where maybe you have an interaction in your model, and you know how complicated that can get. Well, here you're just going to have to go back to the hardcore program in the equations and do it that way. That's why we took the time in chapter 2 to do that kind of stuff, because you should be able to do it. It's going to be, might be a little bit messy, but you should be able to do it in the end. Any questions? Okay, well, what about contingency tables? If you remember the fiber example, you want to maybe model the counts in that contingency table using a proportional odds regression model. Well, we can do that. And we can get a test for independence too, but you have to just be a little bit careful about what the alternative hypothesis actually means. So our null hypothesis model under independence would look like this. So again, you're modeling the logit of the cumulative probability, and you set it equal to beta j0. Notice that x is not in there at all. That's because x is independent of y. Then the alternative hypothesis model, the same, except for now you are including x in there, just like we did with the multinomial regression models, where we have indicator variables representing I minus 1 levels of x. And so our null and alternative hypothesis, then written out, look like this. We'll just substitute those models in there. Now the key here is to realize that, well, what does this alternative hypothesis mean? It means that the way that x affects y is in this ordinal manner that you're specifying here. Note that that is different from what we had with a multinomial regression model, or even with just a regular old Pearson chi-square test for independence, where we didn't specify what kind of dependence existed. Here we are specifying a particular kind of dependence. This ordinal dependence that we have. This actually can be good, because your test can have more power. What does that mean? Everyone remember from the very first stat course what power means. You'll be more likely to reject. Meaning that since you have narrowed down the possibilities for the alternative, you have more power, what would be a better word? More, let's say a higher chance maybe of rejecting independence than you would if you didn't specify what kind of dependence to look for. So you have a narrower alternative, you could say. So you're going to have more power, so that if this kind of dependence exists, you'll be more likely to find it than you would with a multinomial regression model. So in some sense, approaching the test like this, when you do have an ordinal response, is preferred than with the multinomial regression model. Now, of course, there could be situations where you have maybe a different kind of dependence, and this test may or may not pick it up. So that is a possibility, but when would you apply this kind of a test? Well, when you do have an ordinal response, and the way that you're modeling this ordinal response is logical, and so that's why this would work.
What about ordinal responses like the test?
I'm sorry,
what about the ordinal responses
The reason being is because you have a narrower alternative. Now, you're focused on trying to reject for this particular case rather than possibly all possible cases. And because of that, you'll be more likely to find, if there is dependence, you'll be more likely to find that kind of dependence. In a more mathematical way, let's talk about that. Now, what will be the degrees of freedom for this for this test here? What will be the degrees of freedom for this test? I minus 1. Okay? Because notice what you're doing here. You're setting I minus 1 beta is equal to 0. Okay. What will be the degrees of freedom for this test? Oops, don't need that there. Not just j minus 1. I minus 1 times j minus 1. Remember, it's the same as with the regular Pearson chi-square test statistic. Okay, in both cases we can find a negative 2 log lambda. Okay, so what would then our chi-square distribution look like when we compare it to a chi-square distribution? Well, your chi-squared distribution looks something like this. And this is not going to be drawn to scale here. And you might also have a chi-square distribution that looks like this. Yeah, the area underneath both those curves is meant to be 1, even though it might not look like it. Again, it's not drawn to scale. The important thing is the shift that you see here. The shift in that chi-square distribution. So the red one, so I'll do a little legend here. Let's see, the proportional odds model. The green one could be then the distribution for the, you chose the wrong green. The green one could be the distribution for the multinomial regression model. Okay. Now, why do you think I drew the green ones essentially kind of shifted to the right? For those of you taking stat 883, think about a chi-square distribution. As the degrees of freedom increases, what happens to the mean? What's the mean of a chi-square random variable? It's equal to the degrees of freedom. Yeah. Is it 2 times the degrees of freedom or just degrees of freedom? I think it's just degrees of freedom. Yes. I'm 95% confident that is correct. For some reason I want to say 2. Maybe that might, I think that's the variance. 2 times the degrees of freedom. Anyway though, so look how the alternative hypothesis, the multinomial regression model will have a higher degrees of freedom, a higher mean. That's why I drew that green distribution shifted to the right. Now, in both cases, we're looking for large values of negative 2 log lambda in order to reject HO. In which case do you need a larger value, the multinomial regression model? So with the proportional odds model, you could potentially reject the null hypothesis with a smaller negative 2 log lambda than you could with the multinomial regression model. So that's more of a mathematical reason why this has more power. And we'll see that in an actual example next. Let's go back to the fiber-enriched crackers example. So last time, or I guess last few times, we have found that there was marginal evidence of dependence. We weren't specifying what kind of dependence with the multinomial regression model, the Pearson chi-square test for independence, but we found marginal dependence. We said 0.026 was the p-value before. Okay, let's look what happens then with this proportional odds regression model. It makes sense to use these kinds of models here because we do have an ordinal categorical response. none, low, medium, and high for the amount of loading. So then our alternative hypothesis model would look like this, where, if you remember, the rows were none, bran, gum, and both. And the way that we had set up our row variable was in that ordering, so that the none category is essentially the baseline category. So we just actually take a look at the data set. Okay, so there's what the data set looks like. And I want to estimate then a model to this data. So here's how I can do it. If you remember that I'm going to use the POLR function that exists in the mass package. So I say then POLR formula equal, floats my response, fiber is my explanatory variable. Also, just as a reminder, too, we can't model the data directly in the contingency table format in R. We have to use a data frame format, just like what we had with the weak data. So this is the actual data format that I'm fitting the model to. Now, in that data frame, you saw the variable called count, because count represents the number of people that fit in each of those categories. So just like with the multinomial regression model, I need to include that. And I say method equal logistic. And so let's go ahead and estimate the model. We'll summarize it. So here is then my corresponding parameter estimates. Let me go back over here to Word so I can draw in here. So for example, this none low represents beta hat 0, 1. So we're basically putting the dividing line between the none and the low. So in terms of these cumulative probabilities. So this would be like for j equal 1. This fiber bran in the coefficients here represents the negative of beta hat 1. So beta hat 1 is actually positive, 0.3859. Shoot, I forgot to do that. So if you notice when I write out the actual estimated model, I put the hat really wide. I had changed my notation throughout my notes, except for there. You can just write the hat on top of the P. I just need some way to note that indeed that this is the estimated model, and I don't think the wide hat really is needed. So we'll put a little hat on the capital P. Again, notice how I write out my model, so I can just write it out essentially in one line. Well, I guess 2 lines, but you get the point. And that is I just simply put beta hat J0 in the model statement itself, and then I write out right after it where beta hat 10 is, beta hat 20 is, and beta hat 30 is. So you have the ANOVA functions available to you to do likelihood ratio tests. And so in this case, I'm just going to use the capital ANOVA function. It's in the car package. My negative 2 log lambda is 15.048. Notice the degrees of freedom, 3. So we're testing 3 betas. Are they equal to 0 or not? And look at my p-value there, 0.0017, well, 0.001776. What this says is that there is strong evidence that there is dependence, where before we only had marginal evidence. That's the advantage of using this kind of a model in an ordinal response setting. Illustrated very nicely there, and that's why I use this example. And the nice thing here, this basically specifies what kind of dependence that we have. We have this ordinal dependence that's occurring there. And you can follow up on this ordinal dependence by looking at odds ratios. I do that in my book just to save time. I'm not doing it here in class because it basically involves the same techniques that we've done many times before. So please make sure to look at the book. You're responsible for that. Okay, are there any questions?
So why do you call this section contingency table?
Well, because we had an original contingency table that we were working with in terms of our data, right here.
Actually, you're testing the dependence.
I'm testing the dependence between fiber and bloat. It's just we had to rewrite the data in a format, so a different format, so that we could estimate the model to it. Okay, so we talk about proportional odds models. Guess what? There's something called a non-proportional odds model as well. And this is what a non-proportional odds model looks like. It looks just like the proportional odds model, except for now notice we do add J subscripts in there for the betas. So you should think, okay, why did I call it proportional odds model before or in the last class? Well, it's because remember, how these odds, had essentially a proportionality constant with it, that e to the, let's say, beta 1, for example, if we only had one explanatory variable. Here now, we don't have that proportional occurring anymore. If you were to simply find the odds using this model, you can see that you have a beta J1, beta J2 in that odds. And so the odds will change then as the J changes too. So that's why it's called non-proportional odds. But what this does then, this kind of a model, it allows us to potentially examine, well, was that proportional odds assumption correct? And how can we test an assumption? Do a hypothesis test. So essentially then, we could focus on these beta terms. With the proportional odds model, these beta terms were all equal to one another for each explanatory variable. So here's what a set of hypotheses then would look like. So imagine, for example, with the example that we just got done with the fiber example, what we would basically be doing is, let's say for the fiber indicator variable, we will be testing, is beta 1, 1 equal to beta 1, we'll be testing beta 1, 1, is that equal to beta 2, 1? Is that equal to beta 3, 1? That's what we would be testing. And then we do that then for the next explanatory variable and the next. In other words, we would do all of them, generally speaking, we would do all of them at the same time. All of your explanatory variables, all those corresponding beta parameters, the regression parameters, you would test for equality across the levels of your response. So note that if you reject HO, well, that says, uh-oh, I have some of these betas that are not equal to one another. This proportional odds assumption doesn't look like it holds. If I don't reject HO, that says, okay, well, at least from this data, I cannot, convince myself that the proportional odds assumption was bad. So, what would you do in that situation? Well, typically just continue using it. That's how you could do this. Again, just a likelihood ratio test. -2 log lambda. What could you do? Well, you could estimate both models, get the residual deviances of both models, and use that to do the test, similar to the long way that we did in chapter 2. Okay. However, there are some issues with doing this, with using these non-proportional odds models. First of all, even though you reject HO, you may still want to use the proportional odds model. And it gets down to, or the reason is because it gets down to, an issue that exists with hypothesis testing. And let me relate it to a simpler setting, just to make sure you've seen this before. Let's say that I am interested in testing the following. We're going to look at a population mean, and suppose this population mean represents the mean GPA of all students on campus. Suppose I hypothesize it to be 3 for some reason. And I'm testing, is it 3 or not equal to 3? Okay, so you would do the test using methods that you've had in other classes. Now let's say that somehow I also truly know that the mean is this. Ideally, you would like to reject HO here, right? Because the mean is not 3.0. But in a practical sense, does it really matter? No. In fact, for any kind of set of hypotheses like this, where you have equal versus not equal, if I have access to, let's say, an infinite possible sample size, I'm going to find some sample size where I'm going to reject HO most likely. Because it would be very unusual for, let's say, the mean to be exactly, if you have let's say, infinite amount of precision, it will be very unusual for the mean to be it will be almost impossible for the mean to be exactly equal to 3 itself. Okay. So, even if I would reject HO, in a practical sense, I don't really care. And the same thing happens here. That likely there will be some sample size. If you could have an unlimited amount of resources and you're able to take as large of a sample size as you want, you're going to be able to reject HO at some point. And so then it comes down to, in a practical sense, is it really worthwhile or not? And so that's why I put that there. But here's even a better reason to be cautious about looking at these non-proportional odds models. These non-proportional odds models could result in the following. Let's just take a look at category 1 and 2. Oops, I drew that incorrectly, or wrote it incorrectly. There we go. The probability that y is less or equal to 2 is actually less than the probability y is less or equal to 1. Why is that a problem? This model says that could happen. And I'll show you an example of why it says it can happen. But why, first of all, is that something that's very undesirable? Yeah. Yeah, in fact, this has to happen. But this model allows for that top portion to happen, that less than. So how do you think this could happen? The model estimates a probability to be less than 0. Of course, probabilities can't be less than 0. Okay, so let's take a closer look at this. So this is my cumulative logit model plot.r program. And I want to do some comparisons here. Let me do a split screen. Let's see. There we go. Yeah, there's a lot of writing. Let's clean it up. Okay. We use this. Let me just double check something. Hold on. Okay. So we drew these plots before with a proportional odds model. in the bottom screen here, using the same program. And what I said was in that particular time, let's suppose that we had the following model. So I set particular values of beta 1, 0, beta 2, 0, beta 3, 0. Looks like a bunch of scribbles up there, doesn't it? And then beta 1 was equal to 2. And this is what we got. Notice that we have this, we always have these cumulative probabilities following the correct order. So for example, let's say x1 equal to 0, come up, the probability that y is less or equal to 1 is always going to be less than the probability y is less or equal to 2, is always going to be less than the probability y is less or equal to 3. So you see the correct order there. Notice that all the probabilities on the right side, the pi sub j's, are all greater than 0. Now let's change things a little bit here. Suppose I use exactly the same model. So I have exactly the same beta j zeros, except for now with a non-proportional odds model, I'm going to allow my beta j 1s to change. And I'm going to set the first one equal to 2, which was what we had for beta 1 in the previous set of plots. But now I'm going to let beta 2 1 be 3, and beta 3 1 be 6. Let's do the plots again using the curve function, and this is what we get. So look at the left plot on the left and compare it to what we had before. So you can see we don't have that nice same shape for all three lines there, unlike what we did before. And so we can see that the lines are actually crossing. And that's actually not good, because what that is saying, like right here, is that the probability y is less or equal to 3 is actually less than the probability y is less or equal to 1. That can't happen. That violates rules of probabilities, you could say. Well, why does that happen? And that's what's illustrated on the plot on the right-hand side. Take a look at for pi 3. That probability actually dips below 0. Not good. So while originally when you saw that non-proportional odds model, you might be thinking, yeah, why don't I just always start with that? Because that's a nice model. It's a more fuller model. If I had to, I can always reduce the model to a proportional odds model. But the problem is that this model violates some of the underlying rules of probabilities. And so that's a problem. Now, if you want to actually estimate then these kinds of models, unfortunately the PLLR package does not work, or PLLR function doesn't work. You have to use the VGLM function to do that. You can see examples of how to do that in my corresponding program. Okay, so lastly then for chapter 3, there are many other models that can be used for multi-category responses. One common one that's used sometimes is the adjacent categories model. What I mean by adjacent categories, take a look what's on the left-hand side of the model. We have pi sub j plus 1 divided by pi sub j. So we're doing the direct comparison, essentially in odds, of comparing category j plus 1 to j. Those two categories are adjacent, thus adjacent categories model. And in fact, one can get that expression for that model by simply looking at the multinomial regression model. Because remember how with a multinomial regression model, the way that was presented in our notes, we did this. Log of pi sub j divided by pi sub 1. And we said, well, what happens if you wanted to compare some other category other than category 1? You just simply rewrite it. Well, this model starts with that, essentially that rewriting, and only looks at then the adjacent categories. So you could estimate the multinomial regression model and immediately come to the adjacent categories model. But one reason why I bring this up, this kind of a model, is that suppose we do have an ordinal response. By looking at the adjacent categories there, that can actually be useful. Because look at you're comparing, let's say, like with respect to the fiber example, none to low, low to medium, medium to high. You see that progression occurring there, and so you could take advantage of that progression by now removing the subscript of the j on the betas, just like what we did with the proportional odds model. And you could use that kind of a model when you have an ordinal response. And again, these models can be fit with the VGLM function. Perhaps I'm typing too fast. Okay, so that concludes chapter 3. Are there any questions?
So is this alternative to the non-proportional?
Yes.
What's that?
Yeah. So this would be another option. There's a variety of different models, and in fact, Alan Agresti, who I guess my book is kind of competing with, because he has a few categorical books out there. He actually has a specialized book for just ordinal categorical responses, and you can look at this in a lot more detail, by taking a look at his book. And there's a variety of different models out there. Proportional odds is the most popular. Not necessarily means it works well in every single such situation, but I can't go over all those models, so that's why I bring that one up, since it's a very popular one.
I think what I'm asking is, will this be, instead of using the non-proportional odd model, the whole problem of estimating negative probabilities, would you rather use this one instead of the non-proportional odd? Deal with the test. What are the betters that equal on that?
Well, so you could use this as an alternative to a non-proportional odds model. You could use this as an alternative to proportional odds model. Off the top of my head, I do not remember if you will get negative probabilities with this model. I don't remember off the top of my head. Are there other questions? Okay. So let's go to chapter 4. So the way that my first 4 chapters of the book are structured is that chapters 1 through 2 deal with a binary response. So binary, so you have 2 categories. I do that first because those are the most, I don't know, I guess I think of them as essentially the most prevalent out there. Then chapter 3 says, okay, in addition to having maybe just 2 categories for response, you could potentially have 3, 4, 5, or whatever. So then chapter 3 looked at then these multi-category response settings. So we've looked at 2 categorical response settings, a binary, multi-category. Now we're going to look at the third type of a categorical response, and that is simply a count response. And what I mean by count, and we've actually kind of looked at counts before with respect to binomial data. How many successes did you have out of n trials? The key was you always knew how many trials there were. So you have an upper bound for what that count should be. Here, we're going to look at count responses where we don't have that upper bound. So where can this occur? Here are some examples. So the number of credit cards an individual owns. Well, you might hope that there is an upper bound, but really there isn't. As long as those credit card companies keep on sending you stuff in the mail, you keep on getting more and more and more and more. There's not necessarily where you're doing, let's say, an experiment of, let's say, sending in your credit card applications out of a certain number of trials and seeing how many you get. If you just keep on sending them in, send them in, send them in, that's why there's not necessarily an upper bound. Number of arrests for a city per year. Well, it depends upon where you live, of course, but there isn't an upper bound. You're not, let's say performing, let's say, an identical experiment a certain number of times, and I'm trying to observe the number of successes. The number of people arriving at an airport at a given day. You have a general idea of what it would be, but there's not necessarily an upper bound. Let's say, like when the Berkshire Hathaway meetings come into Omaha, Look at the Omaha airport, what happens there those few days. There's a lot of people that are coming in. The number of cars stopped at the 33rd and Holdrege Streets intersection. So that intersection, let's see, kind of disoriented. I think it's that way over there. You know, that way? You sure? I'm used to teaching this class over in Hardin Hall, which, of course, that's where the Department of Statistics is, and that's obviously if I'm in Hardin Hall, I know where 33rd and Holdrege is. I'm not used to on this part of this campus to know where it is. So over there, you know, how many cars are stopped at that intersection? Or you can think of any kind of intersection. You know, there's not necessarily an upper bound. Number of people standing in line at Starbucks. This is an actual problem that my wife has because she likes to go to Starbucks every day and pick up her coffee. And there's not necessarily an upper bound there. So for these particular settings, then, we're not going to use a binomial distribution. Instead, we're going to use a Poisson distribution. So we're measuring counts without necessarily an upper bound. All of you should have seen a Poisson distribution before in like a steady or one-line course. So the actual Poisson distribution part will not necessarily be new. What we will do, though, is first review the Poisson distribution. We'll look at some simple settings, just like what we did with Chapter 1 for a binary response, just like what we did at the beginning of Chapter 3 for a multinomial response. And then we're going to slowly extend it to a case where maybe you have explanatory variables associated with that Poisson response. Let's see. Also, in this introduction here, this is something that definitely comes up with a Poisson with these count settings. Is that is, excuse me, you might want to control for other items that are not necessarily explanatory variables. So, for example, you know, number of arrests in a city per year. Well, let's say you want to do some comparisons between New York City and Omaha. Well, New York City is going to have more arrests than Omaha, probably just simply due to, well, there's a lot more people living in New York City than there is Omaha. And, you know, the number of people there is not necessarily an explanatory variable, but you want to control for it. And so we'll look at how you can control for it in a Poisson setting. Okay, so let's talk about some basics. So here's the Poisson probability mass function that all of you have seen before. My random variable is denoted by a capital Y. Possible values that my random variable can take on are denoted by a lowercase value, lowercase y. And those possible values are 0, meaning a 0 count, 1, a 1 count, and notice I don't specify an upper bound. And on the right-hand side, we see the actual function, e raised to the negative mu, mu is a parameter, times mu raised to the y power over y factorial. This mu parameter is greater than 0. As a little bit of a shorthand notation here, I can say y is distributed Poisson mu, or Po mu. So let's look at some properties of a Poisson random variable. So one can show, you would do this in a Stat 882 course, so you've probably done this, that the expected value of y, meaning what would you expect y to be on average, happens to be equal to that mu parameter. So the mean of y is mu. That's why the letter mu is often used as that parameter in a Poisson probability mass function. Also, interestingly, the variance of y happens to be mu as well. While that simplifies everything for us, it also can be very restrictive too. And we'll look at what that means. Should I do it? Yeah, actually I do mention it here. What can often happen is that your observed value of, let's say your sample variance can be greater than your sample mean. And what that means is that you are actually observing more variability than what you expect if this Poisson distribution actually held for your data. That's what's called over-dispersion. The word dispersion is often means like disperse in terms of variability. Over means, well, more than what you would expect. And so we're going to have to look at ways to account for over dispersion, and we'll hold off on that until chapter 5. If the y's are independent, let's say maybe I go observe some counts, and I see first I get a 2, next I get a 5, next I get a 3. And if all those counts were independent, then the sum of the y's, that distribution ends up being Poisson n times mu, which kind of makes sense. If each of these y's had the same distribution to begin with, then what will be then the overall distribution for the sum of them? Well, take the means times your sample size. If the means were all different, well, then just simply sum up the means. But what's my likelihood function? We looked at likelihood functions for a Poisson, for a binomial, for a multinomial. Here for a Poisson, let's say I take a sample size n, I'm interested in estimating the mean. Well, again, just like what we've done before, you take the product of all the probability mass functions, and there you go. So that y sub k represents maybe, let's say, the kth observation. K is equal to 1 to n. Similar to what we saw in section 1.1 with the binomial distribution. You can take the derivative of the you could first of all find the log of the likelihood function, take the derivative with respect to mu, set that derivative equal to 0, solve for mu to get the maximum likelihood estimate, and you will get mu hat as the maximum likelihood estimate, and ends up being the sample mean. That's something you would do in like Stat 883. I'm not going to ask you to do that though here. Also, with respect to, remember those nice little properties in section 1.1 that I stated for maximum likelihood estimators? Well, they all hold true here then too. And that is, for example, the estimated variance of my mu hat. Well, again, you can use the second derivative of the log likelihood function, expected value, invert it, you do all the math, you get mu hat divided by n. What's the approximate distribution for mu hat for a large sample? Normal, yeah. Normal with a mean of mu, and the estimated variance is mu hat divided by n. Okay, well, why could that be useful? Let's say I want to do a wall confidence interval for mu. Tell me what that interval should be. What should I start off with? Mu hat? There you go. Voila. We have a confidence interval for mu. What have we learned about these kinds of confidence intervals? Yeah, they might not work as well as we would like. If I have a large sample size, it would be fine. But for small sample sizes, it's probably not going to work as well as we would like. What about the lower bound? Now remember, mu has to be greater than 0. Can this lower bound potentially be less than 0? What do you think? Is there anything restraining it from being less than 0? No, there's not. That's obviously not ideal then. What would be a simple fix to the problem? Well, yeah, that would be a simple fix, yes. I'm actually looking for a better fix. A better than the simplest fix. What do you mean by standardizing?
Standardize your mu hat.
Any other ideas? And what did we do in chapter 2? We did something to our pi to guarantee it was always going to be between 0 and 1. We took a transformation. Okay. What do you think would be a good transformation here? What?
Exponential.
Exponential functions. Or how about we talk about the inverse of that? How about we find a confidence interval for the log of mu first? So we find log of mu hat. Let's do a Wald interval. So it's z 1 minus alpha divided by 2 times the square root of the estimated variance of log of mu hat. Right? Okay. Once I get that, then put a little e down here, and now I am guaranteed to have an interval that's always between 0 and whatever the upper bound is, or infinity, which is what the range of mu is. So that's a simple fix. How would you find, now this is more, well, while non-stat majors are welcome to answer this, but I hope stat majors, hopefully you've talked about something like this already in Stat 883, if you're just taking it now. How would you find the log of mu hat? I'm sorry, the estimated variance of the log of mu hat. What technique could be used? We've actually used it many times in this course. Delta method, yes. So I'm not going to expect you to do this on the test, but the delta method is such a useful tool, and I think it's useful just to bring it up here because you can see how easy to use. Obviously, Appendix B in my book talks about it in detail, or somewhat in detail. Okay, so I want to know, well, what would be the estimated variance of log of mu hat? This is how the delta method works. It's actually based upon a Taylor series expansion, if you've ever heard of Taylor series expansions. I won't get into the details behind it, but it's very simple to apply. So you take your estimated variance for mu hat that you calculated before, and you multiply it by the square of the, the first derivative of your transformation. And let's evaluate this at mu equal mu hat. That's all you would do. That's very simple. So what is the partial derivative of mu for log of mu? In other words, I want this. I know calculus isn't a prerequisite for this course, but I think most of you have had it. Yeah, 1 over mu. I'm going to evaluate it at mu hat, so we're going to put 1 over mu hat there. I'm going to square it, take it times what's the estimated variance of mu hat? Mu hat over n. So what am I left with? Oops. 1 over n mu hat. That's the variance that I would use in that confidence interval. Again, I'm not going to ask you to do it on the test, but I might ask you to apply this confidence interval on the test. Now, I wanted to include this in my book, and I believe I'll say this again, I'm 95% confident that we did not include it in the book. And the reason being is my co-author says, well, has anybody actually done research on this interval? Well, I can't find anybody doing it. So because of that, we decided not to include it. You know, people haven't necessarily explored the properties of it. But you know, the little bit of investigations that I've done, this interval is a lot better than the Wald interval in terms of true confidence level. So that's something that you could do. However, it's not necessarily as good as another interval that we will look at. So maybe that's why no one has, at least I can't find anybody investigating it.
I don't know what the Wald.
Well, this is still a Wald. Both these are Wald intervals. One essentially calculates a Wald interval directly from mu. One uses a transformation to get it. Okay, well, what about a hypothesis test for mu? Well, Maybe you want to test, is mu equal to mu 0 versus mu does not equal to mu 0? Well, as you might expect, a wall test statistic would be mu hat minus mu 0 divided by the square root of mu hat divided by n. Use a standard normal approximation of it. A score statistic, remember we talked about a score test in the past, is essentially the same except for this part right here. You put mu 0 in there instead. So how do you think you would decide on rejection of the null hypothesis?
When z is greater than 1.96.
Excuse me?
When z is greater than 1.96.
If z0 is greater than 1.96, reject. How about the other direction? Let's say negative 1.96. That too. I mean, it's a two-tailed test because look at the numerator there. You know, basically you're looking at what's the difference between mu hat and mu 0. The farther they are apart, either in a positive or a negative direction, the more evidence there is against the null hypothesis. So this would be a two-sided or two-tailed test. Use a standard normal approximation. Now, with respect to the score test statistic then, one could derive a score confidence interval for mu. So if you remember the Wilson confidence interval, that was based upon a score statistic. Remember that was in the homework of the derivation. Well, the derivation for this one is in the homework as well. Remember what we found in section 1.1 about score, about the Wilson interval. And that was, it was a lot better than the Wald interval. Well, guess what? This score interval is a lot better than the Wald interval as well, at least the original Wald interval. And this is what the end up result is for that interval. Make sure you take a look at the derivation. Now, unlike section 1.1, since we took a lot of time doing that, I'm not going to show you, true confidence level plots here, but they are in the book. And take a look at those. And similar to what we saw from section 1.1, same thing happens here. So how else do you think you could find a confidence interval for mu? Give me, I can think of two approaches. How do we find confidence intervals for pi? So we did the Wald, well, I guess the Aggressy-Cool, the exact. So you could do an exact interval. And while we didn't get into the derivation of it, I mean, that's okay. We just, with the prerequisites of the course, it's hard to go into all the details always. But one could use the fact that use the Poisson distribution exactly, just like how the binomial distributions use exactly to derive the Copper-Pearson interval. One could derive an exact interval. Take a look at my book for the details. You're not responsible for the exact interval. What would be another method that we looked at for a confidence interval for pi? Well, I mean, use simulation to evaluate the interval, not necessarily to find one. Yeah, you could do a Bayesian. You could. It wouldn't be called a confidence interval, though. It would be called a credible interval. But you could essentially use it the same way.
Likelihood ratio?
Yeah, likelihood ratio. So you could do a likelihood ratio interval. You are responsible for that. It would be more clear how to actually do the computations. So it's not necessarily a closed form solution. It'll be more clear once we talk about Poisson regression models. So stay tuned for that. Okay, so let's get into an example here. This deals with 33rd and Holdrege streets. So this is an old picture. I don't know why I didn't update it in my notes when I just updated it. So here's a picture from my website where I use to explain where my office is. And so we can see that, I'll come back here. Here's Holdrege Street, right here. Here's 33rd Street. obviously, here's my office. I'll just use my mouse here to point. And so we have a stoplight here at the 33rd and Holdrege Street intersection. Excuse me, four-way stoplight. And the reason why I've always been interested in this intersection here, ever since I moved here in 2003, because there's something right here, if you see where my mouse is, that for some reason this map is not portraying as actually having any kind of really dimension to it. There's actually something right here. Does anyone know what's actually right here? The fire station. Okay, so let's take another look at a picture of this. Oops. Here we go. So we have the Quilt Study Center right here. Here's the fire station. Okay, you can see off in the distance we have a red light at that stoplight, at that intersection. We have one car right there, right now, that's stopped. But what happens if we have some other cars? So I'm going to do a little drawing here. Oh, we'll make these cars, oh, this is a big car right here. And we'll do one more to demonstrate my point. I've done drawings like this before, and I, as you know, on my cover of my book, I have some pictures. And as a joke for with my co-author when we were designing the cover, I basically, when I did a drawing like this in the class before, I took a screen capture of it, and I put that as the cover of my book, and he said no. By the way, so we see some cars there. Now let's say that there's an emergency, and here's where, that was a bad color choice. Let me, we'll use blue. And this is where the fire trucks are. So there's an emergency, and the fire trucks need to get out. If there's cars lined up, what's going to happen? There's going to be big problems. Okay? And so that's why, if you see, there's like the sign right here. It says, do not block the driveway. Now, maybe only the stat majors have noticed this, but have you ever noticed that driveway blocked before? Oh yeah. Oh yeah. Cars get backed up. Well, why does that happen? Well, you might be thinking, okay, well, when a car's coming along here, they're going to see that sign, and they'll realize, okay, yeah, I'm not going to drive, over to that driveway. But as you can see here, there's a tree, and that tree kind of overhangs, especially during the summer. And because of that, you typically don't see that sign until almost it's too late, and you don't have enough time to stop before you hit that intersection. So, perhaps people who are in transportation might be interested in this. At least for me, from a statistical point of view, I'm interested in knowing, well, on average, how many cars would be stopped at this intersection? Because this will tell me, especially if I'm, let's say, a city planner, this would tell me if I need to watch out and maybe redesign some stuff here to deal with the fact that these cars could be blocking the driveway for the fire station. So, in a very simplistic manner, what one could do is find, first of all, a confidence interval for mu here. Maybe use that, which we will next time, use that then to come up with a probability for what is the probability that this intersection will be blocked and the fire truck couldn't get out. Okay. Let's see here. So it's my estimation based upon the typical length of a car. It would take, I know I say this someplace. It would take 9 vehicles to fully block that driveway, which is really not that much. And so as we will see next time, I actually collected some data. Sounds like this would be a great project for a grad student to work on. Instead, I did it. It was a number of years ago before I was tenure, so maybe that's why I did it. I was feeling like a grad student. I actually watched the intersection for 40 minutes, and for every stoplight cycle, I counted the number of cars, the maximum number of cars that were stopped there. And so like the first time I did it, I got 4. Next time 6, and so on. So what we will do is next time is we'll analyze this data and see if that fire station has truly indeed something to worry about. Are there any questions? Okay, that is it for today.